Hello, my name is Jason Chonko and I'm the Applications Marketing Manager at SIGLENT Technologies. In today's video, we're going to take a look at serial decoding capabilities of the SDS series of oscilloscopes. Specifically, we're going to be looking at the I2C bus in a small Raspberry Pi project using the SDS 2304X. And that is a 300 megahertz 4-channel oscilloscope with 2 gigasample per second sample rate, as shown here in this cutaway. And what we're going to be taking a look at is the I2C bus for a temperature measurement, and then we're going to be writing that temperature to an OLED. So as we pan down to our experimental setup here, we can see the breadboard with the temperature and humidity sensor, the OLED, and our Raspberry Pi here off to the right. And so then we're going to show a little bit more about the wiring configuration and get more into the oscilloscope itself. Here we've got some leads coming out of the GPIO bus, running over to our breadboard, and here you can see the display. Again, that's an I2C OLED display with a S-clock and the SDA lines. And now you can see the BMP 180 pressure sensor. Both of these are from Adafruit, 3 volts, S-clock and SDA. And as we warm up that sensor, it's going to adjust. Now, adjust the temperature. This particular setup has a sample rate every 5 seconds. It's going to pull that temperature sensor. So it isn't the really fast update rate, but for temperatures, just really wanted to take a temperature measurement every 5 seconds and relay that to the OLED display. Here is the OLED that we are using, again from Adafruit, and our pressure sensor. And here is a closer look at the wiring diagram that we have. And you can see the pinouts and all of the connections that we've made. And now we're going to connect the SDA line and S-clock lines up to the oscilloscope using some fly lines here, just make sure everything's still working. And there we go, get a nice temperature update. And now we'll connect our oscilloscope probes. Here we'll connect up to the fly line with ground, probe number 2, and we're going to connect, remember, a clock to channel 1. And we're going to have the data connected to channel 2, and we're going to enable channel 2. We've got a rolling auto trigger. Let's reposition that. We're going to change that auto trigger to normal, so it will only show us something if it meets the trigger criteria. And now let's take a closer look at the trigger configuration. We're going to set the trigger type to serial. We're going to check the protocol off as I2C, and that's going to give us some options for the signal. We've got source clock selected as channel 1. Here we've got a number of other selections. We're going to set the threshold, which is very much like the trigger voltage value. Select channel 2 for data and set the threshold for channel 2. Now we can take a look at, wrong button. Take a closer look at the trigger setting. We have a number of conditions that we can select. We're just going to go off of the start condition. This means that if the start bit is available, it will be part of that trigger condition selection. And now let's zoom back out. We're going to expand our, we're going to shrink our time, or expand our time base a little bit and get more of this, more of the full communication burst. Put the instrument into stop mode so we can do a little analysis on each of the captured waveforms. Just going to zoom in a little bit, and now you can see the clock on top and all of the bits as well as the data. Zoom back out and start the scope back up again. Now we're going to go to the acquire menu, and I want to show you what happens when we set our memory depth. So right now our memory depth is set fairly high or deep. Now let's go to a shallow memory depth. So that you could see the resolution is going to be fairly poor at this rate. So what we've done, really there's a balance between the memory depth and the horizontal time base so that we can get the largest horizontal resolution or time-based resolution, and also the largest sample time. So there's an interplay there. Once we have the trigger stabilized and we have the memory depth stabilized, we can go to the decode menu. And the decode menu is going to allow us to do some on-screen decoding. We're going to enable decode 1, set the, very similar, we're going to set the protocol to I2C. We've got a number of selections here available. We're going to change our signal, again, source clock 1, threshold, again, very similar to the trigger. We want to have a threshold configuration. And the SDA we'll select as channel 2, set the threshold, very similar to the trigger, but this is for decoding on screen. Now we will set, we could select a different address bit type, and we can turn the display on or off. You can see the blue dots at the bottom, or blue boxes down at the bottom. Each of those is going to hold the actual raw data, and we can also turn on a table here, the decoding table that provides some more helpful information. We can also scroll through each entry in the decode table, and each of the boxes, the blue boxes on the bottom, has its own entry in the table, so we can take a closer look at the table for each individual entry for data returns or reads or writes. We can also change the format type. In this case, we're just going to stick with hex, but we also have ASCII, binary, and decimal. And we'll back out. And now we can go back to the decode type, turn that off if we want to actually have the list off. And the sample rate and the sample depth are shown at the top. Again, we want to optimize it. The more data that we can collect at a higher resolution, the more likely we are to successfully be able to decode. Here we've got the expansion of the horizontal time base, then shows us each of those individual bits. You can see here we've got the clock and data, and now we've got, as we go out further, you can see the screen resolution doesn't allow us to see each individual word. We can also use the horizontal zoom by pressing the horizontal scale, and now we can zoom into each individual slice and move that slice back and forth in time and take a look at each individual transmission as it's sent back and forth from the instrument or from the I2C peripherals that we happen to be working with. And we can move that around to various parts of the waveform or of that transmission or that burst. Here we're just going to key in on one of the first two bursts, and here you can see that is that's a read and a write. And we'll go into that in a little bit more detail here in the next few seconds, and then we can expand back out again. Now we're going to turn that decode list or decode table back on and take a closer look at some of that. You can see that we've got the actual packet number, the time that it happened, as well as the address that we were reading or writing to, read or write function, and then the actual data here, the first line. We can scroll through that list as well. First line's showing all of that data. So you can see throughout this list we've got an address of 77H, which is hardware, and we've got also a 3C, and we've got reads and writes denoted by W's or R's. Here we're going to take a look at the Python code, and this is actually sending a command to the BMP or the temperature sensor and asking for temperature data, and then we're going to do that every 5 seconds as well as update the display. Here I've run a little program called I2C detect for the Raspberry Pi, and you can see that we have a device at 3C and at 77, which is what we had seen in the table previously. Here we've got addresses at 77 and 3C. And now we'll look at a little, here is the Python code that's calling the temperature sensor. You can see that is at 77. And here are some of the headers for the registers for the data. And you can see they also match the headers that we have on the other side of the table. So we've successfully created a number of peripheral connections with I2C devices, and we've troubleshot some of those connections using an oscilloscope, using some of the serial decode features. And here we're going to summarize some of the decoding features that we've used in this particular project. Use an auto trigger mode to get the data on the display, then adjust the horizontal and vertical scale and position such that you can see all of the signal of interest. You're going to want to get everything, start with some data on the display and then adjust as you go along, and that will help, especially if you don't know exactly what you're looking for. That'll help at least get some data on the screen, and then we can adjust further as we proceed. The next step is going to be to use that serial bus triggering to establish a stable trigger and also isolate that signal segment that we're looking for. For example, start bit, failed acknowledgement bit, or other types of segregation for that trigger setup, and then set the trigger to normal. Now it's only going to show you that particular segment that meets all of the trigger criteria that you've established prior to capture. Then to get long bursts of data, you're going to want to maximize that memory depth length. And then you want to adjust the horizontal scale to get the largest value that still provides a decent sample rate, providing enough resolution for you to properly decode the bits, as well as see any particular elements of the bits that are transferred back and forth, or the digital signals that are being transferred back and forth. With that, you have to have a high enough resolution to be able to see those details. You also may enable on-screen decoding and a decoding list or table to see each individual packet and the data that's being transferred. And finally, we want to collect bursts using a long time-based scale and single trigger to help freeze that update. If you have a bursted or a bus that's continually talking, you're probably going to want to isolate single bursts so that you could do some analysis on each one individually instead of continually updating. So if you set it to single trigger, it's only going to take a single picture as soon as that trigger criteria is met. And then use the horizontal zoom to pan through each individual bit or packet. Again, the idea, if you have the RAID oscilloscope with deep memory, you'll be able to capture a long time base with high resolution and also be able to then analyze each individual decoded packet that way. We hope that you enjoyed this particular video. If you have any questions, please contact your local SIGLENT office. Thanks again and have a great day.